computer number format is the internal representation of numeric values in digital computer and calculator hardware and software. Normally, numeric values are stored as groupings of bits, named for the number of bits that compose them. The encoding between numerical values and bit patterns is chosen for convenience of the operation of the computer. The bit format used by a computer's instruction set generally requires conversion for external use such as printing and display. Different types of processors may have different internal representations of numerical values. Different conventions are used for integer and real numbers. Most calculations are carried out with number formats that fit into a processor register, but some software systems allow representation of arbitrarily large numbers using multiple words of memory. Binary number representation: computers represent data in sets of binary digits. The representation is composed of bits, which in turn are grouped into larger sets such as bytes. A bit is a binary digit that represents one of two states. The concept of a bit can be understood as a value of either 1 or 0, on or off, yes or no, true or false, or encoded by a switch or toggle of some kind. While a single bit, on its own, is able to represent only two values, a string of bits may be used to represent larger values. For example, a string of 3 bits can represent up to 8 distinct values as illustrated in Table 1. As the number of bits composing a string increases, the number of possible 0 and 1 combinations increases exponentially. While a single bit allows only 2 value combinations and 2 bits combined can make 4 separate values and so on. The amount of possible combinations doubles with each binary digit added as illustrated in Table 2. Groupings with a specific number of bits are used to represent varying things and have specific names. A byte is a bit string containing the number of bits needed to represent a character. On most modern computers, this is an 8-bit string. Because the definition of a byte is related to the number of bits composing a character, some older computers have used a different bit length for their byte. In many computer architectures, the byte is used to address specific areas of memory. For example, even though 64-bit processors may address memory 64 bits at a time, they may still split that memory into 8-bit pieces. This is called byte addressable memory. Historically, many CPUs read data in some multiple of 8 bits. Because the byte size of 8 bits is so common, but the definition is not standardized, the term octet is sometimes used to explicitly describe an 8-bit sequence. A nibble is a number composed of 4 bits. Being a half byte, the nibble was named as a play on words. A person may need several nibbles for 1 byte from something. Similarly, a nibble is a part of a byte. Because 4 bits allow for 16 values, a nibble is sometimes known as a hexadecimal digit. Octal and hex number display. Octal and hex are convenient ways to represent binary numbers, as used by computers. Computer engineers often need to write out binary quantities, but in practice writing out a binary number such as 100101101010001 is tedious and prone to errors. Therefore, binary quantities are written in a base 8, or octal, or, much more commonly, a base 16, hexadecimal, or hex, number format. In the decimal system, there are 10 digits, 0 through 9, which combine to form numbers. In an octal system, there are only 8 digits, 0 through 7. That is, the value of an octal 10 is the same as a decimal 8, an octal 20 is a decimal 16, and so on. In a hexadecimal system, there are 16 digits, 0 through 9 followed, by convention, with A through F. That is, a hex 10 is the same as a decimal 16, and a hex 20 is the same as a decimal 32. An example and comparison of numbers in different bases is described in the chart below. When typing numbers, formatting characters are used to describe the number system, for example 00000B or 0B0000000 for binary and OF8H or 0xF8 for hexadecimal numbers. Equals converting between bases equals. Each of these number systems are positional systems, but while decimal weights are powers of 10, the octal weights are powers of 8 and the hex weights are powers of 16. To convert from hex or octal to decimal, for each digit one multiplies the value of the digit by the value of his position and then adds the results. For example, representing fractions in binary equals fixed point numbers equals, fixed point formatting can be useful to represent fractions in binary. The number of bits needed for the precision and range desired must be chosen to store the fractional and integer parts of a number. For instance, using a 32-bit format, 16 bits may be used for the integer and 16 for the fraction. The 8's bit is followed by the 4's bit, then the 2's bit, then the 1's bit. The fractional bits continue the pattern set by the integer bits. The next bit is the halves bit, then the quarters bit, then the 1/8 bit, and so on. For example, this form of encoding cannot represent some values in binary. For example, the fraction, 0.2 and decimal, the closest approximations would be as follows: even if more digits are used, an exact representation is impossible. The number, written in decimal as 0.3333333333, continues indefinitely. If prematurely terminated, the value would not represent precisely. Equals floating point numbers equals, while both unsigned and signed integers are used in digital systems, even a 32-bit integer is not enough to handle all the range of numbers a calculator can handle, and that's not even including fractions. To approximate the greater range and precision of real numbers, we have to abandon signed integers and fixed point numbers and go to a floating point format. In the decimal system, we are familiar with floating point numbers of the form 1.1030402 105 equals 1.1030402 100,000 equals 110,304.02, or, more compactly, 1.1030402e5, which means 1.1030402 times 1 followed by 5 zeros. We have a certain numeric value known as a significand, multiplied by a power of 10, known as an exponent. If we have a negative exponent, that means the number is multiplied by a 1 that many places to the right of the decimal point. For example, 2.3434e-6 equals 2.3434a, 10a6 equals 2.3434a, 0.000001 equals 0.0000023434. The advantage of this scheme is that by using the exponent we can get a much wider range of numbers, even if the number of digits in the significand, or the numeric precision, is much smaller than the range. Similar binary floating point formats can be defined for computers. There are a number of such schemes. The most popular has been defined by Institute of Electrical and Electronics Engineers. The IEEE 754-2008 standard specification defines a 64-bit floating point format with an 11-bit binary exponent, using excess 1023 format. Excess 1023 means the exponent appears as an unsigned binary integer from 0 to 2047. Subtracting 1023 gives the actual signed value, a 52-bit significand, also an unsigned binary number, defining a fractional value with a leading implied one, a sign bit, giving the sign of the number. Let's see what this format looks like by showing how such a number would be stored in 8 bytes of memory, where S denotes the sign bit, X denotes an exponent bit, and M denotes a significand bit. Once the bits here have been extracted, they are converted with the computation, A2-1023. This scheme provides numbers valid up to about 15 decimal digits, with the following range of numbers. The specification also defines several special values that are not defined numbers, and are known as nans, for not a number. These are used by programs to designate invalid operations and the like. Some programs also use 32-bit floating point numbers. The most common scheme uses a 23-bit significand with a sign bit, plus an 8-bit exponent in excess 127 format, giving 7 valid decimal digits. The bits are converted to a numeric value with the computation, A2-127, leading to the following range of numbers. Such floating point numbers are known as reals, or floats in general, but with a number of variations. A 32-bit float value is sometimes called a real 32, or a single, meaning single precision floating point value. A 64-bit float is sometimes called a real 64, or a double, meaning double precision floating point value. The relation between numbers and bit patterns is chosen for convenience in computer manipulation. 8 bytes stored in computer memory may represent a 64-bit real, 2 32-bit reals, or 4 signed or unsigned integers, or some other kind of data that fits into 8 bytes. The only difference is how the computer interprets them. If the computer stored 4 unsigned integers and then read them back from memory as a 64-bit real, it almost always would be a perfectly valid real number, though it would be junk data. Only a finite range of real numbers can be represented with a given number of bits. Arithmetic operations can overflow or underflow, producing a value too large or too small to be represented. The representation has a limited precision. For example, only 15 decimal digits can be represented with a 64-bit real. If a very small floating point number is added to a large one, the result is just the large one. The small number was too small to even show up in 15 or 16 digits of resolution, and the computer effectively discards it. Analyzing the effect of limited precision is a well-studied problem. Estimates of the magnitude of round-off errors and methods to limit their effect on large calculations are part of any large computation project. The precision limit is different from the range limit, as it affects the significand, not the exponent. The significand is a binary fraction that doesn't necessarily perfectly match a decimal fraction. In many cases a sum of reciprocal powers of 2 does not match as a specific decimal fraction, and the results of computations will be slightly off. For example, the decimal fraction 0.1 is equivalent to an infinitely repeating binary fraction, 0.0001100011. Numbers in programming languages. Programming in assembly language requires the programmer to keep track of the representation of numbers. Where the processor does not support a required mathematical operation, the programmer must work out a suitable algorithm and instruction sequence to carry out the operation. On some microprocessors, even integer multiplication must be done in software. High-level programming languages such as Lisp and Python offer an abstract number that may be in expanded types such as rational, bignum, or complex. Mathematical operations are carried out by library routines provided by the implementation of the language. A given mathematical symbol in the source code, by operator overloading, will invoke different object code appropriate to the representation of the numerical type. Mathematical operations on any number are whether signed, unsigned, rational, floating point, fixed point, integral, or complex are written exactly the same way. Some languages, such as ReXX and Java, provide decimal floating points operations, which provide rounding errors of a different form. See also, binary coded decimal, binary numeral system, gray code, hexadecimal, numeral system, octal. Notes and references. The initial version of this article was based on a public domain article from Greg Gerbel's vector site. External links, online char, hex, binary, base 64, etc. Encoder-decoder, useful computer numerals.